Hey everybody, this is your review for Test 3 for PHY 2020 in spring of 2023. So just general overview. Our Test 2 coverage stopped with finding the magnetic fields using the Biot-Savart law and Ampere's law, so this Test 3 material will pick up there. Remember that the ray optics info is all extra credit. It's an extra credit homework, it's extra credit material, completely bonus. And so it's not going to be covered on Test 3 or on the final exam. Your format will be the same as previous tests, and you're allowed to bring in a 3-inch by 5-inch index card as an equation sheet. Remember that I'll give you the constants sheets that I've given you all semester. Remember also that I don't really care about what your answer is. The number is unimportant to me. So you have to show your work to receive full credit. If you don't show sufficient steps, I might not give you all the credit that you're due, especially on things like proofs. Test 3 is our last day of class. Your final exam is May 11th at 8. Remember that we're not going to have any reworks on Test 3. So if you score higher on your final exam than you do on Test 3, then I'll replace that grade. But I won't do that for any other tests because you've had the opportunity for reworks on Tests 1 and 2. I'm not going to post a separate online review for your final exam because all of the Test 1, 2, and 3 reviews are already posted and recorded. So if you want to go back and look at any specific material, you can just look at those reviews, or you can look at the recorded lectures for any of the material if you feel a need for a refresher. Okay, so now into the material. One of the first things that was covered after Biot-Savart law and Ampere's law was the Lorentz force law. And the Lorentz force law tells you how particles move, how charged particles move in electric and magnetic fields. So that equation is that the force on a charged particle moving in an electromagnetic field is equal to QE plus QV cross B. So remember that charged particles move parallel to electric field lines. However, they're going to move perpendicular to their magnetic field lines. The force will be perpendicular to the magnetic field lines. Also remember that static electric fields and static charged particles, they'll still feel a force, but in order to feel a force from a magnetic field, a charged particle has to be moving. So one of the ideas or applications that comes from this is that if you have a charged particle, say for example it starts off here at the bottom moving to the right with a velocity v, then remember the right hand rule will give you the direction of the force on that charged particle. So we had two, we had stop in the name of love and we had the gun, but either way you take your right hand and you point your index finger, for example, in the direction of QV, you point your middle finger in the direction of V, and then your thumb is the direction of the resultant force, so that's the gun. Alternatively, you can point your right hand fingers in the direction of QV and then rotate your palm towards the magnetic field and your thumb will be the force. And that's the stop in the name of love, okay? So you can see here that for a positively charged particle with a velocity to the right in this magnetic field, which is into the screen, that you'd have an upward force. And then as your trajectory changes, then that would cause, for example, this particle to move in a circle, okay? So what this is saying is that, for example, if the circular motion is provided by the magnetic field force, then if your particle is at right angles to your field, then if the motion of your charged particle is right angles to your field, then the angle in between QV and B is 90 degrees. And so your magnitude QV cross B, which would be QVB sine of theta goes to 1. See, then you can set that equal to your centripetal force. And then that, remember, centripetal force is mv squared over r. In those cases, then your charged particle makes circles in these magnetic fields. And the radius of that circle would give you the charge to mass ratio, as you can see here. Now, if your particle is not moving at right angles to your magnetic field, if it has a component of its motion along the direction of the magnetic field, then that motion would remain undisturbed. So for example, here the magnetic field is in the x direction. The particle entered that magnetic field. It had a component, a velocity component along the x. That component remained unaltered, so it continued moving the x direction. and then the perpendicular components to the field caused it to make circles. And so that makes a helix, okay? So just remember all that. And we did some problems, homework problems associated with helical motion in magnetic fields. Okay, another thing that we talked about was the Hall effect. So in this one, if you have a current carrying conductor and it's placed in a magnetic field, then what's going to happen is those free charge carriers in the metal will feel a force as they move through the field. Here you have a magnetic field which is into the screen, as shown here with the axis. So your magnetic field's into the screen. And so your charged particles moving through that magnetic field would move to opposite sides, as you can see here, of your current carrying wire or bar. And that establishes a voltage perpendicular to the direction of current flow, as you can see in this schematic. And this is known as the Hall effect. And it's because the charge carriers are going to be deflected to one side of the conductor as a result of that QV cross B magnetic force that it experiences. And then what's going to happen is the charge is going to build up perpendicular to the direction of current flow until the electric field established due to that voltage that's created due to that separation of charge is enough to balance out the magnetic field force. And so you can set the QV cross B force equal to the electric field force, and then you can solve for what the voltage is. Remember that the voltage is related to the field. If it's a constant electric field, you just multiply the distance that the field acts over to get the voltage. So you have VD is equal to ED, which is equal to your Hall voltage. You can also solve and get this equation for the Hall voltage. Your Hall voltage is equal to the current density J divided by NQ, where N is the charge carrier density, Q is the charge on the charge carrier, B is your magnetic field, and D is the width of your Hall probe there, and then that's going to equal to your Hall voltage. Okay, we talked about the transformation of electromagnetic fields due to the motion of frames. So remember that we said that electric fields and magnetic fields are really flip sides of the same coin, because you can just do a simple transformation from a stationary frame to a moving frame, and you can transform an electric field into a magnetic field and vice versa. So let's take our moving frame to be the prime frame, so that's S prime, and it's moving at a constant velocity with respect to the stationary frame, say for example V. We call our stationary frame S. Then we can see that B prime, which would be the magnetic field according to the moving frame, would be equal to B minus 1 over C squared V cross E, right, where B and E are the magnetic and electric fields respectively as measured by the stationary frame. V is the relative velocities of the frame, and C is, of course, the speed of light. And then we can also see that E prime is equal to E plus V cross B. And so what you can see is that you can, these ideas of electric and magnetic fields can be interchangeable because of the motion of the frame. And remember that we proved at the end of all this that C is equal to 1 over the square root of mu naught epsilon naught. Okay, Faraday's law. Faraday's law of induction states that the EMF induced in a circuit is directly proportional to the time rate of change in the magnetic flux through the circuit. So that means, mathematically, that we use this curly E, cursive E, or epsilon, if you would. The EMF is equal to minus N times d phi b dt. Phi b here is the magnetic flux, which is shown here as the integral of B dot dA over the surface, okay, over the surface. And N here is the number of turns in the loop. So let's just say that you have a circuit with a little current loop, and the current loop is like a solenoid or something like that. It has N numbers of turns. A is the cross-sectional area of that current loop, okay, and then B would be the magnetic field through the loop. Okay? Now, we can write this out as the EMF would be equal to the line integral of the electric field around that closed loop, E dot ds, is equal to minus N d phi b dt. Okay? In differential form, we did the derivation to take this from the integral to the differential form. This can be written as del cross E is equal to minus partial of V with respect to t. And that's Faraday's law in differential form. So to discuss this law, you can induce an EMF in different ways. Basically, you just have to have a changing magnetic flux with time. And so what that means is that you can change the magnetic field with time, like from a varying current, because currents create magnetic fields. So if you have an AC current, that creates an AC magnetic field, and that can induce an EMF. Or you can have the area of the loop change with time. So for that, we talked about motional EMF as an example and some others. Okay, and then the other is, remember that the magnetic flux is the dot product between the magnetic field and the area vector, and the area vector points perpendicular to the plane of the loop. So if you vary the angle in between the magnetic field and the area vector, then that can also cause a changing magnetic flux. And then, of course, any combination of those things can do that for you. Now, Lenz's law is the minus sign in Faraday's law. So remember, here's Faraday's law. The EMF is equal to minus N d phi b dt2. The minus sign is that Lenz's law. And basically, what it's saying is that the induced current in a loop is in the direction that creates a magnetic field that opposes the change in the flux through the area enclosed by that loop. In other words, it wants to maintain the status quo, and it will induce a current in a loop so that the status quo is maintained. Okay? All right, we talked about self-inductance. So magnetic fields are generated that oppose the change of magnetic flux via a back EMF. That's basically Faraday's law. This induced EMF is always going to be proportional to the changing magnetic flux. So that means that if you have, for example, a current loop, currents create magnetic fields, okay? And so if you had a current loop that had a current that was changing in time, then that would cause a magnetic field which is changing in time, and that magnetic field would cause a magnetic flux which is changing in time, and that magnetic flux induces an EMF. This EMF is a back EMF that opposes the change, okay? So instead of writing it in terms of magnetic flux, you could write it for a changing current situation as being proportional to the rate of change of the current. And that constant of proportionality that sets these two back EMFs equal to one another is called the self-inductance L. So we can write that the back EMF is equal to minus L di dt, where di dt is the time rate of change of the current, and L is that constant of proportionality that we call the self-inductance of a coil. It depends on the geometry of the coil and other physical characteristics like the number of turns, but it doesn't depend on the current flowing through the coil. You can also have mutual inductance, which is two coils that are sitting near one another, and if one coil has a changing current going through it, then that would cause a magnetic field change, and then that magnetic field change would cause a magnetic flux through the nearby coil. So that's mutual inductance. So remember that we solved for the self-inductance and really the mutual inductance in a similar way. What you do to solve for the self-inductance is to calculate the magnetic flux through the coil, and then your self-inductance is N times the magnetic flux divided by I. Okay. Now this unit of inductance is the Henry. It's the SI unit of an inductor, and 1 Henry is 1 volt times second divided by amp. So this is the idea for mutual inductance. In this semester we covered that in an online flipped kind of way. But this is kind of a little cartoon of it. You can see that coil 1 is creating a magnetic field, which then goes through coil 2, causing a changing magnetic flux through coil 2. So you can solve for the mutual inductance M in the same techniques that you use to solve for the self-inductance. And there's the equation for the mutual inductance. So here it is. It is the mutual inductance M12 of a coil 2 with respect to a coil 1. Okay, so this is the number of turns in coil 2 times the flux through coil 2 due to coil 1 divided by current 1. So the way to find the self and the mutual inductance for coils is the same kind of strategy. First, you find the magnetic field as a function of the current for the object, and if you don't know it already, you can usually use Ampere's law for a high symmetry situation to solve for it. And then find the magnetic flux for the object using the magnetic field you found in number 1. Note that the self-inductance is L is equal to N5 or I, and the mutual inductance expression looks very similar. And then you plug into that expression for the cell for the mutual inductance, depending on what you want to do. Remember that when you're done, you shouldn't have current in your expression. Just like capacitance, it's a function of the physical characteristics of the inductor. So we exploit this idea of an inductance in circuits. The symbol for circuits, for inductors in circuits, is this coil of wire here. It looks kind of like a solenoid. And a circuit element that has a large self-inductance we call an inductor. Solenoids and toroids are really common inductors. And what we're going to do when we do this for circuits is to assume that the inductance of the rest of the circuit is negligible compared to that of the inductor. Okay, but always remember that even without an inductor in it, a circuit is always going to have some kind of self-inductance. We talked about how to treat inductors and resistors in circuits. So this is an example of an RL circuit right here, which has a resistor and an inductor. And then you can see here that we have a switch right here that can go from position A to position B. In position A, if switch 1 is closed, then you have a battery in series with a resistor and an inductor. And so that would be a series RL circuit with the battery. And if you move switch 2 to position B, then you just have an RL circuit with no battery. Okay? So that gives us our two scenarios. Now remember that if you have a battery in the circuit, then what's going to happen is your inductor, when the switch is closed and it first starts receiving current from the battery, it's going to not like that. It wants the magnetic flux to stay what it was, which is 0. So it's going to generate a lot of back EMF at first, and then eventually as time goes on, it'll stabilize. When it stabilizes out, when the switch has been closed to the battery for quite some time, then you're going to have a nice steady current, and it'll be like the inductor's not even there. It'll be like a piece of wire. And then the current in the loop will be the EMF of your battery divided by the resistor, like the inductor's not even there. But before that time, there's going to be an exponential increase up to that max current, which is EMF over R, okay? And so the equation for an RL circuit with a battery in it, for the current in that circuit, is the EMF of the battery divided by the resistance times 1 minus e to the minus t over tau, where tau is the time constant, and the time constant is the amount of time it takes for the current to reach about 63% of its max value, and that's equal to the inductance divided by R, okay? Now, on the other hand, if you have a scenario where the current's been flowing through the inductor for a long time, okay, but then you switch S2 to position B, now what happens is you have an RL circuit with no battery in it. And then what's going to happen is the inductor is going to want to maintain the status quo, and so it's going to want to maintain that current that's running through it, okay? So to do that, it will act as the power source for the circuit. And it can do that because it has energy stored in the circuit. Now, what will happen though is it can only act as the power source for a certain amount of time. There's going to be an exponential decay of the current in the circuit if you don't have a battery in there. And so your current as a function of time for an RL circuit will be I max times e to the minus RT over L, or e to the minus t over tau. Okay, so you'll have a decaying exponential if the inductor has to act as the power source. So remember that the current in RL circuits is exponential. You'll have an exponentially increasing current or an exponentially decreasing current depending on whether or not there's a battery in there. Okay. Also remember that we covered how to handle inductors in circuits. Remember that they act similarly to resistors, which means that in series, your equivalent inductance of a bunch of inductors together is going to be the addition of all those inductors in series. And in parallel, you take the inverse and add it that way. So for example, 1 over L equivalent would be equal to 1 over L2 plus L1 plus 1 over L2 for two inductors that are in parallel. Also remember that you can solve for how much energy an inductor has stored in the magnetic field at any given time. And the equation for the potential energy stored in an inductor is 1/2 Li squared, where L is the self-inductance and I is the current through the inductor at that given point in time. We talked about how energy is stored in electromagnetic fields in general. If you have a magnetic field, the magnetic field can store energy. The energy density, which is the energy per unit volume in the field, is going to be 1/2 v squared over mu naught, where mu naught is that permeability of free space, which is 4 pi times 10 to the minus 7 in SI units. The energy density for an electric field looks very similar to the energy density for a magnetic field. It's 1/2 epsilon naught E squared, where epsilon naught is that permittivity of free space, which is 8.854 times 10 to the minus 12 in SI units. Okay? All right. The next idea that we covered was the displacement current. And what happened was that Maxwell came up with the idea of a displacement current and added it into Ampere's law, which was existing, and it became the Ampere-Maxwell law. Okay? Now, this displacement current can explain how you can have a magnetic field caused by a changing electric field. So the new expression that you'll have then for your Ampere-Maxwell law is in integral form. The integral about a closed loop of B dot ds is equal to mu naught times I enclosed plus your displacement current I sub d. Now you can write this displacement current I sub d as epsilon naught times d phi e dt, where phi e is the electric flux, or the integral of E dot dA over the surface. Okay? And so in full expression there, your integral of B dot ds is equal to mu naught I enclosed plus mu naught times epsilon naught times d phi e dt. So that's the Ampere-Maxwell law. Now you can write that in differential form as well. And if you write it in differential form, then the way it is expressed is that the curl of the magnetic field, or del cross B, is equal to mu naught J plus mu naught epsilon naught times the partial of E with respect to T. Here J is the current density, okay, and E is the electric field. We did Maxwell's famous derivation for the speed of light in a vacuum. And that derivation involved having the Ampere-Maxwell law and Faraday's law taken together to show that the speed at which electromagnetic waves travel is the speed of light. And it led Maxwell to predict that light waves were a form of electromagnetic radiation, and he also showed that light can exist at any frequency, not just visible light frequencies. This achievement was so remarkable that we now call the 4 fundamental equations of electricity and magnetism Maxwell's equations in his honor. Okay? So Maxwell knew that light was a wave. This had been proven through some experiments with interference and diffraction. And so what he did was, to do that derivation, assume that fields are real things and that they can exist independently of source charges in empty space. And remember that in empty space, the charge and the current are both zero. So from Maxwell's derivation, we showed that the speed of light c is equal to 1 over the square root of mu naught epsilon naught, where mu naught and epsilon naught are those two fundamental constants. We also showed that the magnetic field magnitude for light is equal to the electric field magnitude divided by the speed of light. We also saw that through this derivation that this is kind of a little pictorial representation of what light looks like. It propagates in a direction indicated by the black arrow, for example, and then the electric and magnetic fields will oscillate perpendicular to the direction of propagation and also to each other. You can see here that the electric field, which is depicted in blue, is oscillation direction is perpendicular to the propagation direction and also to the magnetic field, which is depicted in red. To describe this mathematically, we introduced the idea of the Poynting vector. The Poynting vector S is defined as 1 over mu naught times E cross B. Okay? Now here, the electric field and the magnetic field propagation directions or oscillation directions are indicated with orange and green arrows. And you can see that if you take the cross product using the right-hand rule of E cross B, then the direction of the Poynting vector S is going to point in the direction of propagation for the electromagnetic wave. Okay? We define the wave intensity, and it is the time average of the Poynting vector over one or more cycles. Remember that an intensity is a power divided by an area. And so intensity, which is equal to the time average of the pointing vector we showed, is equal to CB naught squared over 2 mu naught, which is equal to C times U average, where U average is the average energy density, and B naught, for example, is the amplitude of the magnetic field oscillation. And you can also write this in terms of the electric field oscillation as well. We introduced the idea of the polarization of light waves. The direction of polarization for a light wave is the direction in which the electric field is vibrating. So shown here, the light is polarized in the y direction, okay? Light can become polarized by different mechanisms, including absorption, scattering, reflection, and things like that. So we talked about polarizers and the law of Malus, and it says that the intensity of a polarized beam transmitted through another polarizing sheet varies as the new intensity is equal to the intensity when it hits the sheet times the cosine squared of the angle, okay? Remember that if you have unpolarized light incident on a single polarizer, then the polarizer is going to halve that initial intensity. Okay, so that's kind of a whirlwind tour of some of the important equations and concepts that we covered since test 2. Please do go back, do the practice test, review concepts that sounded a little or felt a little shaky to you. Happy studying, and I'll see you in class.